So in homework 9, we have this result which is kind of similar to the theorem that we've been taking apart, 3.2.4. Similar in the sense that it involves taking a triangle and then drawing in some lines that are parallel to sides of the triangle, right? And then from that construction, deducing a similarity result. So in this, we begin by taking the triangle ABC and trisecting the side BC. So we place 2 points in here, P and Q, in a way that BP and PQ and QC are all the same length. So we trisect that side BC. And then from each of those 2 points of trisection, we draw in a line which is parallel to the, let's call it the opposite side of the triangle. So through P, we'll draw the line L, which is parallel to AC, and through Q, we'll draw the line M, which is parallel to AB. And with that as our only information in this problem, what we're supposed to conclude is that we have a pair of similar triangles, namely that ABC, so the big triangle that we started with in the first place, is similar to AXY, where X and Y are the intersection points of these parallel lines with the opposing sides of the triangle. So we'd like to show that the orange triangle and the green triangle are similar. And so this is not an obvious, it's not obvious how to do this out of the chute with sort of the basic tools that we have, but what, if you've started on a proof of this, what are some of the things that you've tried so far? So following the hint, if you extend these two lines L and M, they're going to meet at a point which is, in this example, south of our triangle, down here. And so Sabrina, you said you called this point S. Okay. S. And then you're treating L as a transversal to what again?
I said that L is parallel to AC and M is like the transversal to that.
M is the transversal to L and to AC?
Yeah.
Okay. Okay, and then what did that get you?
Making PSQ equal to QYC.
PSQ, this triangle, equal to QYC, this triangle. Equal in what sense?
The angle. I said the angle. So like
the angle.
PSQ is equal to QYC.
Okay, so
and
you
that's
have
technically opposite interior angles.
Yes, right. So treating treating M as a transversal to L and to AC. We have theorem. What was the theorem? The opposite interior angle theorem. 131. I think you're right. 131 says that if we have a set of parallel lines and a transversal to those two parallel lines, then opposite interior angles are congruent, and so we have that pair of angles that we know are congruent. Okay. What then happens from there? What additional congruencies can we get from the same argument?
Well, we can use L as a transverse. L is a transversal, so it's going to say the same thing. It's going to say...
Treating L as a transversal to what?
We can also say...
So last time, M was a transversal to L and to AC, the parallel lines L and AC. Right, so taking AB and M as our set of parallel lines, and L is a transversal to AB and M. I'm going to try and sketch these in here. So L as a transversal to M and to AB, whereas in 131 we used M as a transversal to L and to AC. And again, L and AC are parallel to one another. M and AB are parallel by construction. And so, Theorem 1.3.1 tells us that opposite interior angles are congruent, and so the angle BXP and PSQ are also congruent. So we have now 3 angles in this figure that are all congruent to one another. Okay. What else can we get? What other angles or other things can we conclude are congruent? Anyone see more congruent angles here? So one additional pair of congruent angles that we can get is from the observation that AYSX is a parallelogram. Why is it a parallelogram? Because it has...
AY is equal to X.
Well, we don't know that the lengths are the same.
You have two pairs of parallel sides.
Yeah, you have two pairs. That's the original definition of parallelogram, remember. Two pairs of parallel sides. So AYSX, just to sketch that in here, because that's a parallelogram, we know that in a parallelogram, what's true about opposite angles? They're congruent. That was also a theorem, we should get the reference for. Theorem 2. Okay, so theorem 2.3.5 will tell us that the opposite angles are congruent. So if we draw those congruency marks in here, that means that this angle is congruent to this angle. Oh, but that angle we already labeled with a congruence mark, so we can just put another of the same up here. So now we have 4 different angles in this figure that are all congruent. And then the other pair you were telling me about was the other pair of opposite angles in this parallelogram. That pair is congruent as well. Okay? So the parallelogram that we labeled is not the only parallelogram in this figure, we suspect. In fact, by treating XY as a transversal to L and to AC, we can invoke Theorem 131 yet another time. Theorem 131 with XY as a transversal to... And this is maybe not the most efficient pathway toward the proof, right? We're just trying to figure out what all are we able to say. L and to AC. Again, that's a pair of parallel lines by construction. And applying that, we get another opposite interior angle congruence. I'm going to use a 3/ on that. That we can get PXY and XYA to be congruent according to that. And we can also get the other pair of opposite interior angles to be congruent. This pair here, which I'll do 4/ on. 4 and it's kind of messy. Wait a minute, that doesn't even look right. The last congruence mark that I can make on here is when you look at sort of the angles that are going on around X over here. Right, so we know that AXS, this bigger angle with the double slash on it, is congruent to AYS, again, double slash, and that each of them is partly made up by the triple slash, right, which are the same as one another. And so that also means that AXY is congruent to SYX, right? The remainder of those angles must be the same because they both have to, in turn, add up to AXS. So this angle and this angle are congruent. So we have a whole lot of congruent angles on this diagram. But you were just telling me that now we have enough congruent angles that we can start to make congruency arguments about triangles. Right. So give me some congruent triangles that we can pluck out of this figure.
Well, then you would say that, yeah, X, Y, X.
So AXY and AXY and SXY are congruent, and that's by angle side angle, right? Where the angles are the ones that are marked here, angles with 4/ and 3/, right? And the side is the side XY, right? Which is common to both triangles, so clearly congruent. Okay, so there's one pair of congruent triangles. Okay, what does that do for us? Can we prove that these 3 little triangles are congruent? We know that if their corresponding sides are respectively BP, PQ, and QC, then those corresponding sides are already congruent. So if I have one side that I know is congruent in a pair of triangles, what's the most expedient way to get the rest of the information we would need to show those triangles are congruent? If I have a corresponding side.
Don't you want to use a theorem? Isn't there a theorem that explains that?
There's a congruency criterion
Yeah.
that says that if I have one side that I know is congruent, what else do I also need? I need the angles. Yeah, I need the angles on either side, right, in order to use ASA. So let's see if we can find, if we can make the argument about the opposite angles angles adjacent to these congruent sides in these triangles being congruent. So what can you tell me about BPX and QPS? So this angle and that angle. Vertical angles. What theorem is that?
That's like the first one.
Literally the first one that we ever proved. 1.2.1? Yeah, I want to say it's 1.2.1. So yeah, that seems like it should get us somewhere. Now I've got to go to congruent angle number 5. So 5 and 5, that's a V, Roman numeral 5. Right, so vertical angles, theorem 1.2.1.
Saying that, and then you can do the same thing for the other one too.
And you could do the same thing for the other one. So 6, VI, and VI. Okay. All right. All right, so far so good. So if we're looking at PQS now, we have one side, PQ, which is congruent to two other sides that we'd like to know something about. We also have two adjacent angles, angles marked 5 and 6 in this example, that are adjacent to that side. My 6 doesn't look like a 6. Let me fix that. VI. There we go. So angle 5 and angle 6. Problem is, right now, angle 5 is in one of our other little triangles, and angle 6 is in the other of our little triangles. So what's the last thing we need to do?
For both of them. You have to do
Theorem. I'll help you out with this one. 133 implies that the total sum of angles is 180 degrees. And therefore, having two congruent angles in a triangle guarantees the third angle is congruent as well. And so this angle and this angle have to be congruent not congruent one to another, but they have to total 180 degrees. And in the triangle on the left, we have angle 1 and angle 5. In the triangle on the right, we have angle 1 and angle 6 already in there. And if the total sum of both of those has to be the same, 180 degrees, then it means that the remaining angle in each case is congruent. So we have an angle 5 in the triangle on the right and an angle 6 in the triangle on the left. We could write that out with algebra if we wanted to, and just kind of write it like that. Angle 1 plus angle 5 plus something is 180 degrees. And then also angle 1 plus angle 6 plus something is equal to 180 degrees. And all we would have to do this algebra is just subtract the second equation from the first. The angle 1s are going to cancel, the 180s are going to cancel, and we find out angle 5 minus angle 6, or no, sorry, that the angles that fill in these blanks are going to cancel, which probably means it's not what I wanted. Setting the equations equal to one another instead. Angle 1 plus angle 5 plus whatever has to equal angle 1 plus angle 6 plus whatever. And so filling in angle 6 here and angle 5 there balances the two equations. I made more of that than we needed to. So now, in these triangles, we have angle 5 and angle 6 adjacent to a side which is congruent. And so angle side angle gives us the congruence of those triangles as well. And that's a lot of information. BXP is congruent to PSQ is congruent to, I'm being kind of sloppy on my ordering here, CQY, again, by angle side angle. And so we end up getting a lot of congruent sides in this diagram that we can leverage as well. And with all that information, should be enough to get you over the line to showing that we have similarity in these two triangles. But not only that, and this is an observation that, Jill, you made a minute ago, was that not only are we going to be able to prove that these two triangles are similar, we're going to know what their similarity constant is. Right? We're going to be able to know, for example, that AXY, because XY does end up being congruent to PC for reasons we still haven't proven yet, but we could. That means that XY is 2/3 the length of BC. And so we're going to get a 2/3 proportionality between these triangles. So this is like the midline theorem, except now instead of being the midpoints of AB and AC, X and Y are the 2/3 points of AB and AC. And so we get a 2/3 similarity in the example of this triangle.